As a senior engineering consultant, I'll frame this not as sensational geopolitics, but as a deep dive into the engineering marvel and the brutal physics trade-offs behind rapid global military power projection. Specifically, we'll focus on the military tech angle, the tiltrotor aerodynamics and logistics of the V-22 Osprey, combined with the heavy lift capabilities of the C-17 Globemaster, which enable this kind of surge deployment in a contested theater like the Middle East amid ongoing strikes. Imagine you're an engineer tasked with moving 2,500 heavily armed Marines, plus their vehicles, ammo, and sustainment gear, halfway around the world in under 2 weeks, into a hot zone where airfields might be threatened and sea lanes are contested. On paper, this shouldn't be feasible without massive, vulnerable staging bases. The fundamental constraint? Newton's laws and fluid dynamics. To lift mass vertically requires enormous power, but to move it efficiently over distance demands low drag and high speed. Helicopters excel at hover, but burn fuel at horrific rates in cruise. Fixed-wing aircraft are efficient in flight, but need runways. For decades, that either-or force compromises, slow insertion, or exposed logistics hubs. Enter the tiltrotor concept. It promises both worlds, but physics doesn't hand out free lunches. Visual, archival footage of early V-22 prototypes crashing or struggling in hover. Overlay simple force diagrams showing lift vector versus drag and helicopter versus airplane mode. In March 2026, amid escalating U.S.-Israel strikes on Iranian targets and Tehran's closure of the Strait of Hormuz, the Pentagon redirected the 31st Marine Expeditionary Unit, roughly 2,200 to 2,500 Marines, from Pacific waters near Japan toward the Middle East aboard the USS Tripoli amphibious assault ship and escorts. This isn't just troop movement, it's expeditionary warfare engineering at scale. Marines specialize in rapid insertion, amphibious landings, embassy reinforcement, or securing key terrain. The driver? Time. In a conflict where Iranian missiles and drones threaten fixed bases, you need forces that can arrive fast, self-sustain briefly, and project power without relying on vulnerable ports or airfields. Supporting this, V-22 Ospreys for vertical assault from ships and C-17 airlifters surging heavy equipment like armored vehicles and ammo pallets from U.S. bases. Visual. Map animation showing USS Tripoli's route from near Taiwan to the Middle East, 10-14 days transit. Parallel C-17 flight paths from CONUS to theater, cut to stock footage of Marines loading JLTVs onto C-17s. The physics constraint, 2 to 4 o'clock. Why is rapid deployment so hard? Start with power requirements. In hover, helicopter mode, lift equals weight. L equals 1/2 rho v superscript 2 ACL, but for rotors, it's thrust from accelerating air downward. The disk loading, the weight per unit rotor area, dictates power. High disk loading, small rotors, heavy aircraft, means massive induced power losses per the momentum theory. Power is almost equal to weight caret 3/2 / SQRT 2 rho A. Traditional helicopters keep disk loading low for efficiency, but that means big, slow rotors, limiting forward speed due to retreating blade stall and compressibility on advancing blades. Max cruise, 150-180 knots. Fixed wing? Lift from wing scales with velocity squared, so once airborne, induced drag drops dramatically. But you need runways or catapults. The impossible barrier. Combine vertical lift with airplane efficiency without exploding complexity or fuel burn. Visual, side-by-side CFD simulation, helicopter rotor wake and hover, vortex ring state risk, versus tiltrotor nacelle transition, graph of specific fuel consumption, SFC, versus speed, helicopter high and hover / low speed, fixed wing low at cruise. The V-22 Osprey solves this with tiltrotors, prop rotors that pivot from vertical, helicopter, to horizontal, turboprop airplane, after takeoff. Why does this have to work? In airplane mode, the large prop rotors act like high-bypass turboprops, high disk area, low disk loading in cruise, giving airplane-like efficiency, cruise, 240-280 knots, twice a helicopter's. The rotors are driven by cross-shafted engines, If one fails, power transfers via interconnect drive shaft, a mechanical redundancy rooted in basic torque equilibrium. Transition is the magic. Nacelles rotate 90 degrees in 12 seconds, converting thrust vector while maintaining lift. Aerodynamically, it's boundary layer management on steroids. Blown wings during conversion increase effective lift coefficient. Paired with C-17 Globemaster, 170,900 pounds payload, short field capable, runway 3, 500 feet loaded, powered by 4 high-bypass turbofans for thrust-to-weight that allows steep climbs out of contested airfields. Together, ship-based V-22s insert troops rapidly, C-17s deliver the heavy tail, vehicles, fuel bladders, via air bridge. Visual: exploded 3D view of V-22 nacelle/tilt mechanism, showing gearboxes, drive shafts, and prop rotor hubs. Animation of conversion sequence with airflow vectors. C-17 loading sequence, chaining JLTVs, pallets rolling in, graph comparing range/payload. V-22 versus CH-53 versus C-130. But real engineering is compromise. The V-22 is heavier than equivalent helicopters due to gearboxes, complex, high maintenance, vortex ring state, and prop rotor instability caused early crashes, interconnect drives, and conversion actuators. Fuel burn in hover/conversion is 2-3x higher than cruise. Operating cost: $20,000, $24,000 per flight hour historically, driven by maintenance and fuel. C-17? Massive fuel thirst for global reach. Specific impulse lower than commercial jets due to military thrust margins. Logistics chain vulnerable. Tankers needed for ultra-long hauls. Skeptically, claims of revolutionary speed ignore that transition is risky in high winds or dust. Availability has hovered 60-70% in past years due to component wear. It's not magic, it's physics traded for capability. Visual: graph of V-22 flight hour cost versus legacy helicopters, reliability/availability bar chart over time, side-by-side fuel burn comparison in modes. Is this viable long-term? Yes, for high-value, time-critical missions like this 2026 surge. The V-22 and C-17 enable distributed operations in contested environments, reducing reliance on fixed bases. But costs are astronomical. Sustaining an MU deployment runs hundreds of millions in fuel, parts, and maintenance. Economically, it's only scalable because the U.S. invests in global power projection. For most nations, prohibitive. Final thought: human ingenuity bends physics, but never breaks it. The Tiltrotor and strategic airlift show we can push the envelope of what's possible, trading complexity and dollars for speed and reach. In a world of limits, that's as close as engineering gets to defying them. Call to action: like/subscribe for more engineering breakdowns. Teaser thumbnail of V-22 transitioning over desert.